Welcome to this lecture. This is the third lecture of week 2. In the first two lectures of this week, we have discussed the construction of product sigma field, and then on top of the product sigma field we constructed the product measure. And finally, what we have also seen is integration results with respect to the product measure, and under certain appropriate assumptions we have reduced the integrations with respect to the product measure to iterated integrals involving the individual measures in the operation. Without further delay, we are going to discuss several applications of these results. So, let us move on to the slides. So, let us recall that the Fubini's theorem that we have discussed in the previous lecture allows us to write integrations with respect to the product measure in terms of iterated integrals. That means that you perform the integration with respect to one of the variables or one of the measures first, and then integrate with respect to the other variable. This requires certain appropriate integrability conditions. So, let us just quickly recall them. If your function is non-negative, then you do not require any additional assumptions, but if your function is taking positive and negative values, then your function should be integrable with respect to the product measure. Now, we see several applications. So, let us start with this very interesting application about probability density function for the standard normal distribution. The standard normal distribution comes with these parameters, that mean 0 and variance 1. Here you know that the PDF, the probability density function, is given by this formula 1 by square root 2 pi exponential minus x squared by 2 for all points x in the real line. Now, it is also an important property of the probability density function that this function is non-negative and integrates out to 1. What we are going to do is to verify this fact that this integral is 1, and this will appear as an application of the Fubini's theorem. To simplify our computation, we first ignore the initial scalar 1 by square root 2 pi and look at the integral of exponential minus x squared by 2 and call it I. Now, remember, this is a nice function, nice continuous bounded function, and here if you perform the Lebesgue integration, meaning with respect to the Lebesgue measure, then it will match with the usual Riemann integrations. So, we first go from the Riemann integration to the Lebesgue integrations, and here we recall the setup that the two-dimensional space where we take R2 together with the Borel sigma field and the two-dimensional Lebesgue measure can be identified in the product space structure as R cross R, BR tensor BR and lambda tensor lambda. So, these structures we have discussed in the previous two lectures, but now we appeal to the Fubini's theorem and look at I square. What we will do is that we will just repeat these two integrals, but with two different free variables. In the first integral we will use the free variable small x, in the second integral we will use the free variable small y. Now, you appeal to the Fubini's theorem and use the fact that your integrand are non-negative to club it together to lambda tensor lambda integral, and here you will now have the domain space of the integral to be R cross R. Now, what is the function we are integrating? It is now exponential of minus x squared plus y squared by 2 with respect to the two-dimensional Lebesgue measure, and the domain of the integration is whole of R2. Now, observe that the two-dimensional Lebesgue measure is essentially this Riemann integration, two-dimensional integration dx dy, and now we have identified I square in terms of this integration. Now, we simplify this final integration in terms of polar coordinates, meaning we transfer x to r cos theta and y to r sin theta. So, if you perform this change of variables, then you will end up having the integral I square written in this form, that now the integral range for r goes from 0 to infinity, theta goes from 0 to 2 pi, and x squared plus y squared by 2 becomes r squared by 2, that reduces to this, and dx dy, the change of variable, you know the Jacobian transformation formula, it will give you r dr d theta. Now, if you simplify it further, you will end up with 2 pi. Now, I square turns out to be 2 pi, and therefore, 1 by square root 2 pi of I actually is 1, but I was exactly exponential minus x squared by 2. Let us just go back to that formula again. Since I was exactly exponential minus x squared by 2, the 1 by square root 2 pi of that is exactly equal to 1, which is what we have proved, and this proves that integral of the standard normal PDF integrates out to 1. This is a very nice application of the Fubini's theorem. But let us move on and discuss another important property in terms of certain moments. So, we start with this important proposition that we start off with a non-negative random variable x. We mean non-negative in the sense that the probability of the event x greater or equal to 0 has full mass. So, therefore, probability that x takes negative values is 0. Then let us look at this statement. We say the expected value of this non-negative random variable can be written in terms of this integral, where we are integrating from 0 to infinity of these tail probabilities. But remember, these tail probabilities can be written in terms of the distribution function as 1 minus the distribution function, since the distribution function is essentially probability of capital X less equals to x at any point small x. So, here we are going to connect the expected value of x, where x is a non-negative random variable, with certain integrability of the distribution function. So, let us see the proof. So, we are going with this non-negative random variable. Now, for non-negative random variables, the expectation, which is the integration of x with respect to the probability measure p, always exists in the sense that it could be a non-negative real number and it could also take the value plus infinity. As a measure theoretic integration, this quantity always exists and may take the value plus infinity. Alright. So, that is what we write first. But then note this number x of omega with probability 1 that we have assumed, this is a non-negative real number. What we do is that we look at this interval 0 to capital X of omega excluded on the right side. Now, if you look at the indicator of that and integrate with respect to the Lebesgue measure, you will get the length of the interval, that is nothing but capital X of omega. So, we have just rewritten capital X of omega as an integration with respect to the Lebesgue measure, and therefore, what we end up having is that the original expectation, that was a single variable integration, now can be written in terms of an iterated integration, with the first integration being Lebesgue measure, second integration being with respect to the probability measure. Now, appeal to the Fubini's theorem. Here we have a non-negative integrand, and what we do is that we exchange the order of the integrations. Now, here we first perform the integration with respect to the probability measure and then with respect to the Lebesgue measure. But to do the integration with respect to the probability measure, we first write the integrand as a function in omega first. To do that, we observe that here small x is always between 0 and capital X of omega, and therefore, we look at this open intervals and capital X omega must be inside. So, this is essentially rewriting the indicator from the previous step to this step, but now the integrand is now written in as a function of small omega, and therefore, we can integrate it with respect to the probability measure. But now, if you perform that integration first, you will end up with exactly this probability, that capital X is greater than small x, which is the tail probability, and the integration with respect to the Lebesgue measure is remaining now. But then again, remember that what we have understood earlier is that Lebesgue measure is essentially an extension of the Riemann integration, and therefore, we can simply remove this Lebesgue measure and write it using the Riemann integration notation. That leads to the proof. And of course, the tail probability you can rewrite if you wish in terms of 1 minus the distribution function. This gives you the link between expectation of x and the tail probabilities in terms of the integrations. This is a very nice application of the Fubini's theorem. But then this result has several possible generalizations, which we discuss one by one. First thing that we point out is that earlier we have written x of omega as the length of the interval 0 to x omega, where x omega side, the right side, was kept open. But if you wish, you could continue to write the closed interval 0 to x of omega. Now the only problem is your capital X of omega, if it is taking plus infinity as its value, then you will have to be careful. But typically the random variables that we will work with are real valued. So then there is no problem looking at this closed bounded interval 0 to x of omega, the length of which under the Lebesgue measure is exactly x of omega. If you repeat the above argument, then you can write the expected value of x as an integration of probability capital X greater or equals to x. Now you will notice that we have essentially added this equality symbol in this description. Now we will say that expectation x essentially having two such descriptions, but there is no contradiction in these two descriptions because the functions probability capital X strictly greater than x and probability capital X greater or equals to x are actually matching for all points except at which probability capital X equal to x is greater than 0, meaning there is a jump at that point. Except at the jump points you will have these two functions being equal, but then the number of such jumps is at most countable, meaning either it is a finite set or countably infinite set. In either case, the equality of the two functions that we have just highlighted agrees on all the points of the real line or specifically on 0 to infinity, except at possibly at most countably many points, and therefore their integrals also agree. So there is no such contradiction when we look at two such representations of expected value of x. Now we have used in this result the assumption that your random variable capital X is non-negative, but now for any random variable x, a general one, it is taking real values. What you can do, you can look at the random variable mod of x. Now mod of x is a non-negative random variable and you can apply this earlier result to mod of x instead of x. Now what will happen is that you can write therefore the expected value of mod of x as this integral, but now instead of x you have to write mod of x in the calculations. More generally, if you use any positive real number alpha, then alpha the absolute moment of this random variable x, that you can rewrite using these tail probabilities where mod of x to the alpha appears in the description. But then you can take alpha root in this relation and you will end up with this interesting representation of the absolute alpha moment of x through this integration representation. And this observation leads us to some very nice identification about the finiteness of these moments. There are several statements that we are going to discuss. The first one is essentially an equivalent condition for the finiteness of the first moment through certain summation of tail probabilities, and when these specific tail probabilities are summable, then this random variable must be integrable. And the generalized version for alpha the absolute moment is similar. It will be written in terms of summability of these kind of tail probabilities corresponding to the random variable mod of x to the alpha. And as pointed out earlier, you can rewrite using the alpha root and you can describe this same event through these probabilities. And again, when this series is converging, then you will get the finiteness of this alpha the absolute moment. And finally, the third part essentially talks about a necessary condition for the finiteness of the alpha the absolute moment. This says that this specific limit in terms of these tail probabilities must be 0, but you have to scale it by an appropriate power here. So be careful with the power, and we will discuss this necessary condition after we prove the equivalence of the first two parts. So let us see the first part. Here we observe that for any non-negative integer n, if you look at the integration of these tail probabilities from n to n plus 1, then this is a decreasing function in the variable small x, and therefore the value attained at the point x equals to small n must be larger. So, therefore, if you dominate this integral over this unit length interval, if you dominate this integral over this unit length interval n to n plus 1, you get this upper bound given by this very specific tail probability. Similarly, using the decreasing nature of the integrand in the variable small x, you will say that the minimum value is attained at the point x equals to n plus 1, and therefore, you will get the lower bound here for the integral. So, you have this lower and upper bound for these integrals. Now, recall that expected value of mod x has this integral representation. Now, if this is finite, this will mean that this integral, which is from 0 to infinity, this can be written as a sum over integrals from n to n plus 1, but then if expected mod x is finite, this must also be finite and vice versa. But then again, each of these integrals has these upper and lower bounds as described earlier, and therefore, you can relate the convergence of this sum of integrals with the convergence of these very specific tail probabilities. Expected value of mod x is finite if and only if these very specific tail probabilities are summable. Similarly, by replacing mod x by x to the alpha, mod x to the alpha, you will essentially be able to get the similar result which is described in part 2. We do not repeat the argument for the sake of brevity. Please check this out. Now, we move on to the third part and prove this very important necessary condition. Now, we want to claim first that this limit has to be 0 whenever we are already given that the alpha absolute moment is finite. To see this, first observe that given the alpha absolute moment is finite, we have by part 2 this series must be summable, but then again as a function in n, the terms in the summation, that is decreasing, but the terms are also non-negative. So, you have a series of positive real numbers, but the terms are decreasing in n. Here you apply to the Abel-Princian's theorem and you will be able to claim that the appropriate limit that you want multiplied by n here inside must go to 0. So, this is a necessary condition. Please check the Abel-Princian's theorem. This is a very nice result in real analysis. So, therefore, this gives you the necessary condition, the first necessary condition as per the result, but then again the second necessary condition follows from the first one just by rearranging the indices here. You can just rewrite the fact that from n to the alpha you can change to n, and therefore, the outer limit will be changed from n to the alpha, and that gives you the other necessary condition as stated in part 3. This completes the verification of this result. Now, we move on to another application of Fubini's theorem, but here we are going to look at volume of the unit ball in the nth dimension, nth Euclidean spaces, n dimensional Euclidean space. We denote the unit ball by un. So, this is the closed unit ball that we are considering. So, this is defined by the collection of points small x in Rn such that the components x1 and x2 and so on up to xn satisfy the property that x1 square plus up to xn square, this addition must be less or equal to 1. This essentially says that the Euclidean norm of the point small x must be less or equal to 1. So, this is a closed unit ball that we are considering, and we are interested in the n dimensional volume through the n dimensional Lebesgue measure. Remember, this Lebesgue measure is defined on Rn with Borel sigma field on Rn. So, just for our notational convenience, we denote the volume that we want to compute as alpha n. Now, first we will state this exercise that will be useful in our computations. This is a very simple exercise which says, if you look at the ball of radius r centered at the origin, so that is this set here, the volume of that is r to the power n times the volume of the unit ball. Please verify this. We are going to use this in the actual computations. Now, let us start the computation for the volume of the unit ball. We first observe that if you take any two real numbers x1 and x2 with the property that x1 squared plus x2 squared is less or equals to 1, then for any integer n greater or equals to 3, you have this property that look at the ball centered at the origin in the dimension n minus 2, but with this very specific radius, that square root of 1 minus x1 squared plus x2 squared is the radius. So, therefore, after squaring you get this relation that summation of the square of the components must be less or equal to 1 minus x1 squared minus x2 squared. So, here you get this ball of this specific radius, and according to the exercise that we have just stated, the n minus 2 dimensional volume of this n minus 2 dimensional ball must be this raised to the power n minus 2 by 2 multiplied by the volume of the unit ball in dimension n minus 2. So, that is a very important observation which we now use in our simplification. So, let us now start looking at the volume of the unit ball in the nth dimension. This is nothing but this integration over the set un. So, we are essentially integrating the constant function 1 over this set. But then again, since we are having a non-negative integrand, the Fubini's theorem allows us to write it as a iterated integral, and in fact what we will do is that we will first perform integration with respect to the first two variables and all the rest of the variables separately. Now, if you look at the innermost integration, which is a n minus 2 dimensional integration, that we have already discussed, and that is exactly the volume of the n minus 2 dimensional ball with radius square root 1 minus x1 squared plus minus x2 squared, which we have computed in this formula here, and we just plug back in that formula and simplify. Therefore, what we will end up having is a relation of alpha n, which is appearing in the beginning of our calculation, and after simplifying this relation using polar coordinates, you can reduce it to this expression multiplied by the volume of the unit ball in dimension n minus 2. So, you have a scalar multiplying the volume of the unit ball in dimension n minus 2. So, this essentially gives you some kind of a recursive relation of the volume of the unit ball in dimension n and dimension n minus 2. Now, remember that in dimension 1 the unit ball is essentially the closed interval minus 1 to plus 1, which has length 2. In dimension 2 the closed unit ball is essentially the ball of radius 1, which is essentially the area enclosed under the unit circle, which is pi. And therefore, if you know these first two values, you can recursively compute alpha n for all high values of n. So, this gives you a nice application of Fubini's theorem in the computation of the volume of the unit ball. So, in this lecture we have seen several applications of the Fubini's theorem, and in the next lecture we are going to finally relate this product measure with the concepts of independence of random variables. So, see you next time. Thank you.